Okay, hello there everyone. What we are looking at here today are some exam style questions on topic 5, chapter 5, which is all about energy in the home on the AQA higher combined physics tier. And our first question here is talking about a washing machine being connected to the mains electricity supply using a cable and a 3-pin plug. And figure 1 is showing us our 3-pin plug. We need to name the materials used in the structure of the plug, give the reason why each material is used. Okay, now for our first thing, talking about the pins here, they are made of metal. They are specifically going to be made of brass. However, you would also be allowed to talk about copper. Okay, so either of those would do. You cannot just get away with using metal. We need to talk about specific metals and why we would use them. And the reason why we'd use brass or copper is because they are good conductors of electricity. Okay, so they are good electrical conductors. The outer case is then going to be made of a plastic. Now you don't have to specify a plastic here, we can just say plastic. You would also be allowed to use rubber or something like that if you did want to specify. And again, this is because it's the opposite of being a good conductor, it's a good insulator. So a good electrical insulator. Now if you talk about heat in any of these answers, heat conductor or heat insulator, you instantly would lose the mark here. Okay, and it's quite a lot for a little 1-mark question, but brass and copper because they're good conductors, and the outer case as plastic because it's a good electrical insulator. And that's question 1. Okay, so moving on to question 1b. We're told the 3-pin plug contains a fuse. The fuse is connected to one of the wires inside the cable. Which one of the wires inside the cable is the fuse attached to? And that's B part 1. We've got 3 parts so far to this question. First thing then, it's attached to the live wire. So the fuse is connected to the live wire. That's the wire in which the current comes into the device. So the current comes from the mains through the live wire and fuse into the device. And so that's where that fuse needs to be in case there's a surge. The fuse is a thin wire inside a closed glass tube. The wire acts as a resistor. What effect does a current through a wire have on the wire? What's going to happen? It's going to warm up. It makes it hot or heats it or something like that. And so the goal here of this fuse is essentially to melt if the current gets too high and break that circuit, which might well come into a later question. B part 3 then, the power of the washing machine varies between 0.7 kilowatts and 2 kilowatts, depending on which part of the wash cycle is operating. Calculate the maximum current drawn from the main supply during the washing machine. From the main supply by the washing machine. The mains electricity supply is at a potential difference of 230 volts. So maximum current. That's most likely going to come at maximum power. That's the way my head's thinking of it. But let's double check with the equation that we need here. The equation is power equals current times voltage. I'm trying to find current, so that would be power divided by voltage equals current. So yep, maximum power is where the current is going to be highest. So one thing I need to double check first, 2 kilowatts. Got to times that by 1,000 first to get 2,000 watts. Convert it. And then I can go ahead and do 2,000 divided by 230, which is going to give me my current. Grab my calculator. 2,000 divided by 230 gives me an answer of 8.6956521. And it goes on and on and on. So I'm just going to round that. How many significant figures have we got? We've got 2, 1, 2. So I'm going to round this to 2, so let's call it 8.7. There isn't a mark here for rounding, but it's always good to round to an appropriate number of significant figures. So 8.7 amps. So I'll probably need something like a 13 amp fuse for this washing machine here. Then figure C shows how, figure 2 shows how the main electrical cable is connected to the washing machine for question C. The earth wire is connected to the metal case of the washing machine like so. So we've got the mains electricity cable which comes in. The earth wire then is connected to the case, and the neutral and live wire are connected to the terminal block as well. If a fault makes the metal case live, i.e. the live wire breaks off and touches the metal case, the earth wire and fuse inside the plug prevent the mains cable from overheating and causing a fire. Explain how. So what we basically need to do is explain the job of the earth wire and how the earth wire stops the live wire from overheating in the mains cable and causing a fire. Okay, so the first thing that we're going to happen, if the live wire comes off and touches the metal case, we are going to get a large current from that live wire to the earth wire. Okay, so the first thing I can say is large current flows from live, didn't need a capital there, to earth wire. Apologies, my pen ran off the graphics tablet there. There we go. So there's my first point. The large current flows from the live to the earth wire. Okay, I could have talked about the metal case there and said large current flows through the metal case, I suppose as well, or current goes from live to earth or something like that. This melts the fuse. Or blow. You can also use the word blow. We often talk about fuses blowing. So this melts the fuse. And then that's it pretty much. We've got 2 marks. How does it prevent it from overheating? Well, the large current flows from live to earth wire, and that melts the fuse, cuts off the electricity supply. You could not use words snap or blow up here. Okay, we have to talk about melting or blowing the fuse. That's the other phrase that we often use. Then last part of question 1D. New research has shown that many people underestimate the hazards of using mains electricity. It is important that people do understand the hazards of using mains electricity. Why? Why is it important that people understand that mains electricity is dangerous? Essentially just to reduce the chance of injury or death. If you are not careful with electricity in your household, it can kill you if you are silly with it and doing things that shouldn't be done. So essentially, any sort of reference to reducing chance of electric shock or death will get you the 1 mark here. Electric shock or death, which is a nice cheery thing to be talking about in this exam question. And that's the end of question 1. Moving on next then to question 2. Describe the difference between an alternating current and a direct current. So 2 types of currents that we talk about in mains electricity. I need to here talk about, my pen's gone off for some reason. I need to here to talk about what the difference is between AC and DC. 2 marks. So 1 for describing DC and 1 for describing AC. I'll start off with DC. DC flows in one direction. And it's as simple as that for your first mark. So direct current flows in one direction. Talking about AC then, it essentially changes direction. Okay, and you have to use that word changes. Okay, so AC changes direction. That is one of the most important words there, changes. You need to use that word. So AC changes direction. And you can talk about how often it does that, or talking about twice every cycle, or you could say constantly changes direction or something like that, but you don't get any marks for talking about frequency here. Okay, moving on next to question 2b. An oscilloscope is connected to an alternating current supply. The diagram shows the trace produced on the oscilloscope screen. Each horizontal division on the oscilloscope represents 0.002 seconds. Calculate the frequency of the alternating current supply. Show clearly how you work out your answer and give the units. Okay, so first thing I need to do is I need to work out the time periods. Okay, I don't have any indication of being able to use something like V equals F lambda for this. It's not really a waveform in that sense. I don't have a speed that I can work with, but I can use the fact that frequency is equal to 1 over the time period. Okay, the frequency is how many times a second it changes direction. The time period is how long it takes for one cycle. Okay, one sort of wave. So if I start here, I've got 1 box, I've got 2 box, I've got 3 box, I've got 4 box. And then I'm back to the start again. Okay, if I started at the top, I've got 1, 2, 3, 4. If I started here, I've got 1, 2, 3, 4. If I started at a trough, I've got 1, 2, 3, 4. So in each case, it's 4 boxes. Okay, and so all I need to do is do 4 times 0.002, which is going to get me 0.008 seconds, and that is our time period. So 1 over 0.008 is going to give me my frequency. So if I grab my calculator, 1 divided by 0.008 gives me an answer of 125 hertz. And that's 125 direction changes per second. I'm going to write hertz on my answer line there because it's not here on the end. Because if I look here, it says give the unit and also show clearly how you work out your answer. But because it says give the unit, that's what makes this a 3-mark question rather than a 2-mark question. And if you had no idea how to do this calculation, but you knew that frequency is measured in hertz, you could drop HZ on the answer line and guarantee yourself an easy mark. Okay? So that's question 2B. Moving on to 2C, what is the frequency of the AC mains electricity supply in the UK? This is one of those things that we just need to know. The answer to this one is 50 hertz. And that is the end of question 2. So, moving on to our final question, which for some reason is question 4. I don't know what happened to question 3. We are shown a fan heater in this diagram, and we need to first complete this sentence. The fan heater is designed to transfer electrical energy as something energy and something energy. So what two energy stores is this fan heater going to transfer its energy to? It's a heater, so the first thing I'm going to think about is heating or thermal energy. So one energy store is going to be heat or thermal, but it's a fan heater. So the other thing it's going to need to do is make things move, make the air move. And the energy I would associate with movement, not sure what happened to that N, my apologies, is kinetic energy to do with movement, motion. So there's my first 2 answers, worth 1 mark each. Moving on to 3-part B. The fan heater is connected to the mains by a 3-core cable. Why are the wires in the cable made out of copper? And then B part 2, why are the wires in the cable covered by plastic? This is very similar to what we were being asked before. Copper is simply a good conductor. You could say electrical, you don't need to here. You can just call it a good conductor. And the opposite then is true for the plastic. It's a good insulator. You could have also said it's a poor insulate, helps if I can spell, doesn't it? Insulator, there we go. You could have also said it's a very poor conductor, which is essentially just the opposite of saying it's a good insulator. Or the same as saying a good insulator, but in a different way, sorry. Then, moving on to part C. You may find this equation useful when answering this part of the question. I've got energy transferred in kilowatt hours, I've got power in kilowatts, and I've got time in hours. The power of a fan heater is 2.75 kilowatts. Calculate how many kilowatt hours of energy are transferred when the fan heater is used for 6 hours. So I don't need to do any conversions here because I'm given my equation and my units are kilowatts, which I've got here, and hours, which I've got here. So no conversions needed at all. All I need to do is do 2.75 kilowatts multiplied by 6 hours, and that will give me my number of kilowatt hours, which is how much energy it is using. But instead of in joules, we have this answer in kilowatt hours, and that's the units we use for energy and electricity usage in the household. So I'm writing kilowatt hours on the line just because it doesn't say at the end, but it does say here number of kilowatt hours, so that wasn't necessary. But 2.75 times 6 gives me 16.5 as my answer. Okay. Then moving on to C part 2. How much will it cost to use the fan heater for 6 hours if 1 unit of electricity costs 7 pence? So here's where our unit, in inverted commas, of electricity comes in. When we're calculating how much electricity we need to pay for and things like that, that's where the kilowatt hour comes in. So 1 kilowatt hour is 7 pence. 16.5, checking the time is the same, 6 hours here and 6 hours here, so I can use the same number. So 16.5 times 7 pence, how much does that cost me? 16.5 times 7 gives me 115.5 pence. So my answer here is 115.5 pence. And then finally, moving on to question 3/4, part D. A fault caused a much higher than normal current to flow in the heater. Describe what happened to the wire in the fuse. Well, here we need to be talking about similar to what we talked about before. It's a 2-mark question, and there's only really one line of answer we need to give, and it's how we talk about that we get ourselves the 2nd mark. So we need to make sure that we're saying it melts, it heats up. Okay, so it heats up. And so breaks or melts. I'm going to put the word melts. In fact, I might as well say both. It heats up and so melts / breaks. And that's where my first mark comes from, saying it heats up, and my 2nd mark then comes from saying what happens when it heats up, and that's where it breaks. Blows up gets 0 marks. Just saying that the fuse breaks gets you 1 mark. But then saying it heats up and breaks and melts, that's where you then get your 2nd mark from. And that's then the end of this question sheet.